all are separate conductors. Altogether there are 5 conductors. Here T and S. What is T and C? S means separate, C means combine. Three phases and neutral. Here my transformer, neutral get earth. Metallic part also earth. Only source in earth. Here not earth. Neutral plus earth coming combined. We call this T and C. What is the problem with T and S? We have to have 5 conductors, one more conductor. It causes severe headache to line designers and also the construction party. Previously it was 4 conductors, now it is 5. The weight, bearing capacities, all the things of the poles have to change. Everything, bobbins, all the things have to change. It's really headache and very costly solution. And as a solution, we implement T and C. What is the problem with that? Problem is this. What happen if what happen with this phase earth? Phase current goes to metallic part and also maybe from human body and goes to neutral to the transformer, and this is the fault path. Got it? But you cannot monitor the fault, because if I1 goes with phase the same I1, though it is a fault or not, same I1 goes to neutral. Got it? So what I have done was, we take neutral here, is here. What we do is, we are not going to connect neutral to our metallic body. We will give a separate part to our neutral knee from the body parts. Then what happens? 50% touch and life got earth. What happened? Current goes to metallic part. Here we have very good conductive part. It will not go to body, and the body actually not go to neutral conductor, go to this separately given path. Correct? So if I1 goes from live, in the neutral it It is not I1, it may be I2. In the earth, it may be I3. Anyway, I1 will be equal to I2 and I3. Yes, should be. But now we have a monitoring part. With this system, if we apply RCCB here, if we have RCCB, what will happen? It will trip. It will monitor the fault. What is the requirement of monitoring the fault in a TN system? If it is not going to go through a human body, what is the requirement? It is not going to go through human body. What is the requirement of sensing the earth fault of a TN system? Let's go back in TT. What happened TT? If there is a person, if space got earth, what will be the fault current path? Fault current will go via this and to the ground, and via the ground to the transformer, and from the transformer this will be the fault current path. If this person touch, what will happen? Because of the impedance of this ground path, this R is very high, so there is a considerable portion goes to human body. There is a considerable portion of fault current goes to human body. So in TT there should be a mechanism of sensing earth fault. There is a leakage, in current will not go to neutral conductor. So with RCCB we can isolate the fault before it creates major damage. It is mandatory, because when in event of a fault, if we touch the metallic body part considerable amount will go to human body. So it is mandatory to isolate. Okay, let's go to this. It is not going because there is a very keen path, very less resistive path for the fault to sustain. It is not even think to go to human body, because in a healthy human, body resistance will be about 1000 ohms. Here it may be 0.05 loop impedance. So the portion goes to human body is negligible. Even though we are struggling to monitor the earth fault with this. Why? That's why these are all equipment. This setup can disturb at any moment. maybe this neutral link can broken, maybe this neutral link can broken, maybe this earth link can broken. What will happen if this earth link broke? What will happen? There's no solution. It will go to our body and act as TT system. It will act as TT system. Go to our body and come to transfer. Can't help. It is the nature of the current. So we cannot keep fault, though it is not harmful to our human life. We cannot keep fault in the system. It is one problem. And if we are going to keep this fault, if we have some sensitive equipment, it will damage. So we cannot keep fault, though it is not harmful to the human system. That's why we need to have a clear mechanism to sense the fault. Good. I think you got my point. Okay. It is about TT and TN systems. Okay. Again, as a completion, we should discuss about IT system. What is IT system is, it is like that. Here my source. This is my line current. Here I go neutral. Maybe source get earth or not, whatever. I don't care. I have proper separation about in electric and physically from source to load. Here my load. Now you know IT system always dealing with a transformer. Here my line and neutral. If I touch the system, what will happen? Nothing will happen. This current will not even think to go to my body, because there should be a complete circuit. That means a closed loop to have a current path. Okay, let's think this load is not there. Only phase I am going to touch. Here it generates current and to earth and to where? Nowhere to go. It electrically separated. Here it is a separate system. Here it is a separate system. The circuit is not closed. No current will go. Even though we have a load, this is the circuit. No circuit with this loop. So no any harm by touching one phase at once. But if you mad enough to touch both, yes, there is a separate closed loop. You will electrocute. So this is IT system, where for completion we just discuss what are the applications of IT system. Shaver sockets. For shaving, for men's, we install sockets in bathroom. In bathroom there is a risk of having water into the electricity, and there may have a risk of electrocution. So we separate the sockets of the bathroom from our main line. So we have IT system shaver sockets. And one common application is welding plant, arc welding plant. we use this IT system to weld. And in operation theaters, in hospitals, what do you think? During operation, it may that operation may be a critical factor of deciding a human life. During operation of 8 hours or 10 hours, suddenly system goes trips. What will happen? Such things should prevent at any cost. So, to prevent such things, to have a system with fault free, we in operation theaters we implement IT system. So, those are the usage of IT system, but IT system is little bit expensive. So you know about the systems now. You can apply. You can think about that system. What will be suit for my system? And going back again, it is important. Let's go to this TT system. In for loop path, you can see the earth is also engaged. The for loop path, the resistance of the for loop path, loop impedance may be always little high, because earth resistance also there, rod resistance there, and the conductor resistance there. But in TN system, fault loop path are very dedicated. Only fault loop path only have conductors. Okay, you are the electrode. Only have conductors. Fault loop. So it is very less resistive. So let's have a very simple calculation. Equal IR. If R goes high, I goes low if this is constant, and vice versa. So what happens in TT, R goes high, very low current, but TN, R goes very low, I goes very high. So very high fault current you can experience in TN system, while you experience very low fault current in TT system. And let's go back to our slides. Depending on the fault current, you have to design earth bonding cable. You have to select earth bonding cable depending on the fault current. If you are going to select 2.5 mm earth cable, that is the most common earth cable in the Sri Lankan system. And if you are going to use TN system, think about fault current will be about 230 amps. Do you think that the cable is enough? Cable has always a current carrying capacity, even whether it is a cable or not. For 2.5 mm cable, it is about current carrying capacity is about 20 to 25 amps. So that cable will definitely blown out if you apply it to TN system, which having that much of high current. So you have to be careful. If you are selecting TN, That's why I told you earlier, maybe the utility engineer ask your design, ask this chart engineer certification, if this system is really safe system to live or not. In TN system, 2.5 is 5 may adequate enough. So design is mandatory. So then first you decide what you do, and of course with TN system there is a high risk of electrocution because of the for loop path. There is a considerable portion goes to your body, but in TN system very accidentally, very rarely, if you are very rarely you will be electrocuted if everything goes wrong only. Almost all the time this is very safe system, but it deals with very high current. In TN, TT, it deals with very low current. So earth bonding cable we have to select based on your protection system, low earth fault protection system. Adiabatic equation. This is adiabatic equation. S equal I square T root or K. This is adiabatic equation. This is the table which we are going to use to solve equations. Okay, let's discuss a little more. Now, some myths is so many even some utilities ask your short resistance. Is it really important? Even in chart engineer certificate, there is a provision to specify the rod resistance. Is it so important? No. Rod resistance is just a part of your system. Let's have a better view of typical TT system. Typical TT system. Here you have your transformer. In the transformer, you get a phase conductor and you get a neutral conductor, and this neutral conductor, that means star point is earth. Here my metallic body part is earth. What is earth rod resistance? Is this earth rod resistance, no? In our utility, in our premises, we earth the system via earth rod and we can measure the rod resistance. But this is light, this is neutral. If a fault happens, this is the fault current path. This is the fault current path. And rod resistance is just a part of that path. So, most important is not the rod resistance, but the loop impedance of the fault current path. What will be the loop impedance? It is the most important part, not the fault current path, not the rod resistance. Loop impedance is this. we can measure the loop impedance and the fault, actually the rotor resistance both with two separate equipment. So if your loop impedance, when going to this in this equation, the R is your loop impedance, not the rotor resistance. So rotor resistance is not important. Maybe 10, 100, 200, 500, whatever. Most important is loop resistance. But we can have a good sense measuring rotor resistance. It is, yes. If our rotor resistance is very high, definitely our loop impedance is also very high. Then let's have an example and then you can understand. Let's have an example. In TT system, if the loop impedance is 50 ohms, if the loop impedance is 50 ohms, if we can measure, yes, of course, loop impedance meters are available, okay? Loop impedance is 50 ohms, fault current is 1 amp. How is that? In TT, we do not let the in TT, if the phase voltage is 230, agree? But if we touch the metallic part, if the voltage rise up to 230, maybe the body parts may harm. So we restrict, we keep 50 volt of touch voltage. We do not let this voltage rise exceed the 50 volt. How we do it? Using the calculations. If this is 50, then loop impedance 50, then what is fault current, allowable fault current? It's 1 amp. Allowable fault current is 1 amp. Then what do I have with my RCCB? What are the ratings? 30 milliamp, 100 milliamp and 300 milliamps. Those are the ratings. So system will definitely trip if the RCCB works before it rise up to 50. Got the point? And I have a play zone from 0 to 1 amp. This is my play zone to trip the system. Before 1 amp I should trip the system to maintain this voltage. Before 1 amp. This is my play zone. I can apply RCCB 30, 100 or 300. Got it? Or I can have another solution. So anyway, I can let the current up to 1 amp through the system. So to clear the fault, okay, that what I didn't discuss. There is a fault clearing time. In RCCB it is about 40 milliseconds. In RCCB it is about 40 milliseconds. for 1 amp, we can apply RCCP. The normally fault clearing time is 40 milliseconds. Okay, that means 1 amp or actually in RCCP, it depends on the rating, 30 milliamp or 300 milliamp. Within 40 seconds, it will trip the system. Bonding cable is normally we are using copper cable. If it is copper, it is thermoplastic 90 Celsius. Thermoplastic means the type of the cable, thermoplastic 90 Celsius. Here we go for 90 thermoplastic range. K equal 86 here. Because cross sectional area larger than 300 square millimeter or less than 300 square millimeter, based on that we can use. Minimum cross sectional area we can count. I is 1, T is 14 to 10 to power minus 3 square root over 86, or you can use if it is you are using K as 100, both square millimeter, very few square millimeter, because very few current goes for very few time. So 2.5 millimeter cable is more than enough. Even this is 100 is more than enough. And again, if we go to this, loop impedance, here loop impedance may vary from 0 to 20 ohms. Here loop impedance may vary from 20 to 200 ohms. This doesn't mean loop impedance cannot exceed 200 ohms. It doesn't mean. There may have very high loop impedances, but the problem is you cannot put a protection scheme against that sort of loop impedance. The fault may sustain for